Today I'm going to talk about our ongoing work on deformable object interaction and contact-rich tasks. Our work has for quite some time been inspired and motivated by the human ability to interact with everyday objects in regular environments. We humans do this by using single hand, two hands in coordination, and we interact with both soft and deformable objects and also in different media such as air, water, and oil. And despite the fact that we do this almost without any mental thinking, many of these tasks are still impossible to demonstrate with the contemporary robotic systems. Now, our work has covered problems such as in-hand manipulation using dual arm planning, and also in-hand grasp adaptation, where we devised various types of control algorithms that can adapt to both the change in object attributes, such as, for example, weight, but also compensate for external disturbances, such as in this particular case, external forces. And what still remains, I think, as a big challenge in the area of robotics is shown in the movie in the middle, which shows how skillful humans are really in interaction with objects. And again, in various types of media, when friction coefficients also change, but also the ability of our hands to adapt to the material and also use both hands, of course, as a tool, but also other manipulate tools at the same time as manipulating objects and so on. Grasping, although studied for quite some time in the area of robotics, is really only a small part, what I would say, of a grasping sequence, which has to do really with understanding scenes and understanding how to actually generate a planned grasp in the presence of obstacles, how to perform grasping, both in terms of doing, for example, motion planning, but also task planning, so how to grasp an object for the purpose of being able to use it for the task. And also then, while holding the object, perform some form of adaptation when we have case of, for example, external forces acting on the object, or for the purpose of actually placing it somewhere in the environment. Now, most of the interaction tasks and the works or the work that we are looking into today focuses on contact-rich tasks. And the difference between contact-free and contact-rich task, of course, is that contact-rich task requires some form of exchange of forces and energy that require dynamic planning, and together with trajectory planning, they also need feedback control, which in most cases needs to be a combination of data-driven methods and analytical approaches. We also need to be able to rely on real-time multimodal perception and control, and we also need to be able to take into account complex physical properties, which in most cases will not be uniform when we interact with items such as, for example, food. Now, state representation learning, of course, is one of the big open challenges in several areas: computer vision, machine learning, and of course, robotics. And it requires to address problems such as task relevance and generalization between the tasks. The algorithms that we develop also need to take into account the embodiment of the robot, and the algorithm should most likely be embodiment independent. We need to be able to rely on the multisensory data and also learning continuously while interacting with objects by taking into account rigid, soft, deformable objects. And for that reason also we need to be able to go beyond considering other types of physical parameters that are not solely the shape of the object. And all of these will require a combination of analytic and data-driven approaches for the control purposes, with addressing problems such as the use of kernels, priors, regularizers, latent space representation, and also to some extent sim-to-real transfer. In our work, we have particularly looked into representation learning from the perspective of what kind of properties or what kind of representations are relevant for the task at hand. And we have looked into physical, geometrical, and topological representation for that purpose. And here are a couple of examples of those works. Today, I'm going to focus on three ongoing works that we are currently dealing with or pursuing. The first one is visual action planning, together with Michael, Martina, Petra, and Anastasia, which is also work that will be presented as a full paper during IROS. Now, one of the big problems in fashion industry is interaction with clothing items, where ironing, folding, and alike tasks may need to be addressed. And these tasks are still rather difficult for a robot to execute. So the particular focus of our work is generation of so-called visual action plan for tasks where there are high dimensional state spaces, for example, considering deformable objects. And by a visual plan, we consider a sequence of images from start to goal. And by the action plan, we consider a sequence of actions that are needed to achieve consecutive transitions, such as, for example, in the application of folding. In this particular work, we rely partially on data-driven methods where we learn from the perspective of having a start and a goal image of a particular task. And we are looking for a low-dimensional representation of a system, which is used then for visual action planning. And for this purpose, we employ latent variable models and look into problems such as how to capture all possible state and the transitions between them to make it viable in terms of planning. And also from that point, a sampling of meaningful states that are going to make the action execution possible. So just as a small overview of the approach, two images starting a flat, having a floating item in flat surface in unfolded state, and then the goal state will be a completely folded state, where our so-called visual foresight model then produces both a visual plan, visual action plan of consecutive sequences of actions, resulting in an image that represents that particular state by using a smart latent representation for generating actions. And of course, two important things to take in mind is, of course, the quality of the samples, how we choose them, and what are the appropriate samples for representing the task, and also what is the structure of the space so that the actions are actually viable. The particular idea is then to present or have the dataset tuple, which would be a combination of two states, the initial state and then the successor state, for which a pair is either viable, there is a viable action that can bring us from one to another. So we call this as an action pair or a no action pair. Again, this work is being presented by Michael at IROS, and I just give you an example here how the system performs. In this particular case, we use a Vexor robot to execute the action. So we have a starting state, and in the upper part of the video, you actually see what is the plan of, in blue, which point should be grasped, and the green, where it should be put, which is represented by what we call the successor state, given the initial state. And as it can also be seen here, we do this by using dual arm manipulation. because it, of course, it's much easier to do it with two arms in order to also make the workspace of the robot larger than it would be if only one arm is used. Again, the citation is on the bottom of the previous slide, so please attend and listen to the presentation during this conference. What we also thought was an important problem regarding cloth manipulation and folding was also to build a benchmark where we considered three different tasks. It's published in Robotics and Automation Letters earlier this year. And the three particular tasks that we look at are unfolding a tablecloth or spreading it over the table, folding a towel, and also fitting the neck of a t-shirt of the mannequin head, which would be kind of like an initial task of actually potentially dressing a human. Another work of relevance for this particular workshop that I would like to say a few words about is learning robotic interaction tasks with stability guarantees together with Shabazz, Pietro, and Hang. Now, the motivation for this work stems back to, I would say, rather classical peg and hole tasks, but also tasks that require, let's say, modeling of the pretty complex dynamics, where the dynamics changes abruptly while the task is being performed. And where recently reinforcement learning has been proposed as a relevant model to encode contact-rich tasks. However, the problem of most of the model learning approaches is they specify only the reward function, and there is no really trajectory planning or feedback control, and not necessarily dynamics modeling, relevant dynamics modeling considered in the work. Our idea or our current work is to use Lyapunov analysis and provide some stability guarantees so that tasks that are not only viable and can be executed, but that also ensure that while the task is being trained and executed, no unallowed motions will actually be performed. So we build upon and extend the iMoji work of Villard et al. From RSS in 2014 by contributing with the stability aware model-free reinforcement learning algorithm, where in particular we look into how we can, by again integrating Lyapunov analysis together with model-free reinforcement learning, how we can generate stability guaranteed reinforcement learning for contact-rich manipulation tasks. And for those that are more interested in the work, it has or it's in print for RALD under this year. The third work that I will spend most time on is robotic food cutting, which is together with my PhD student Ioanna Mitsioni and Assistant Professor Ioannis Karianis, which is on control and interpretability of robotic food cutting. And I'm going to let Ioanna tell you a little bit more about that work. But the idea in particular here is to consider single arm cutting while the object is being fixed, as in these examples here, but where the properties of the object are not known beforehand or are not uniform and need to be considered while the cutting is actually performed.
Hello, my name is Ioanna Mitsioni, and I'm a PhD student in the Division of Robotics Perceptual Learning, KTH Sweden. Today I would like to talk about one part of the work we do with manipulation of deformable objects, and more particularly the work we do with robotic food cutting. So robotic food cutting is in general a pretty challenging task because it is almost impossible to model its dynamics analytically. And that happens because we have a lot of dynamic discontinuities, as a lot of the objects that one typically finds in the cutting task are non-homogeneous, which means that depending on where we're cutting, we're going to get different response. There is huge object variety to take into account. There is a lot of friction, which is notoriously nonlinear, and most of the objects that we use are non-rigid. So a lot of assumptions that we could have made about the interaction dynamics are now immediately violated. The approach we have decided to take in RPL is a data-driven model-based approach. And obviously that means that the first thing that we need to do is to get enough data to fit the model. Now, as is the case in most tasks that involve deformable objects, simulating the interaction is really difficult, and the simulations that are available are not useful enough for us to learn an accurate model of the dynamics. So consequently, that means that everything we do starts and ends with a robot. Now, unfortunately, that also means that everything we measure and everything we want to use is constrained by our hardware. Different robots, different sensors, different control laws to gather the data will result in a different model for the same task. And as an example of this, I would like to show you what a latent space that we're trying to learn and looks like when we just change one assumption about the control input. So on the left, you see the TSNE embedding of a lot of different data sets, cutting data sets of these objects. And here we have made an assumption that the force, the desired force that the system wants to exert, will have an immediate effect on the system. So we'll be able to observe it immediately or reach that force level. And as you can see, gathering data with this results in a not very cohesive latent space with no structure whatsoever. Now, on the right hand, we made a completely different assumption, and that was to model the effect of a control input, including a delay. What will happen will not be immediately observable, but after a little bit. And just by making this assumption, we immediately reach a latent space that is much more cohesive, much more well-defined, and obviously easier to learn in. And so, yes, we did learn. We did a lot of experiments. We showed that learning on that nice latent space and using some specific training techniques, we can get a model that outperforms baselines. But what was most important, the conclusion that we reached from this work was that it is absolutely possible in a content-rich task that we will have similar models when you compare them based on the learning curves that have completely different behaviors when you plug them in online. And that was a big mystery, because when you're just comparing the learning curves and everybody has the same or approximately the same training and validation scores, and then some of them, when they act as a model for the controller, lead the controller to unstable behaviors, it gets a little bit dangerous. So then our basic idea was that since interpretability of deep networks is something that is very useful nowadays, we would like to use interpretability to explain our predictions. Now, unfortunately, when we say interpretability usually means images, because that is the human brain works. Things are obvious to us and we understand something when we can visualize it. But the problem is that the interaction dynamics are inherently not images. They are velocities, they are forces. Those are not in an image format. So that means that we need to build images. And after a bit of deliberation on what are the characteristics of an image that we need to preserve, we concluded that the important parts are that it is two-dimensional, that it's compact, that is visually intuitive to whomever is looking at it, and that it represents the state of the system at that particular point well enough so we can learn from it. And we achieved all of those points by introducing what we call the Kinodynamic Images, which are basically sequences of measurements that we take during a task execution and then transform them into a two-dimensional, compact, intuitive, and useful presentation to learn from. And to give you an example of those, let's go back to the example of cutting. When we are above the object and moving downwards to start the task, there are not going to be any forces. So forces are almost zero, just some noise from the sensor. Control inputs are pretty mild, and then we have a lot of displacement on the axis of motion. That would be this axis. Then when we are normally cutting through the object, so we are sawing to break friction along that axis and then move downwards, we have a lot of displacement on those two coupled axes, and of course forces that accompany them. And then lastly, let's say that we are now in the case where the object is too stiff for the controller parameters we have chosen, and the knife is stuck. Then that can be observed by just looking at the kinodynamic image and noting that there is no displacement, but instead we have very high forces. So after we got that representation and does qualify for what we would like to use it, we needed to couple it with an interpretability model to be able to trace what part of that input led to that output. And we do that by using Radkin, which is just an interpretability method for image classification. So basically it answers the question, if the answer of the network is this class, what led to it? And that works very well for our case as well. For example, here you can see the output of a model that was trained to predict if there is going to be motion in some future time step, so if we're going to get stuck or not. And the answer of the model is that yes, there is going to be motion, and I'm very sure about it because there is a lot of downwards progress on axis Z, and it was right. Now to go back to the beginning and the initial question that we asked is, how is it possible that two models that have the exact same training and validation scores behave so differently? And for this, I'm going to show you this example of those two networks that have been trained with slightly different learning rates, and the only difference in their scores is this one. And so the answer to my question is that they behave so differently because they are looking at different things. The way they reason about their predictions is completely different. For example, I'm going to show you that this network down here pays a lot of attention on the forces on axis X, which is the wrong axis to look at. And just by looking at it and evaluating it this way, we can now tell that when we plug this online with the actual robot, if there is some noise on that axis, it will probably lead to the wrong prediction. Of course, it's not possible to go through every decision the network has made through all the data set and then evaluate it visually, but what you can do is that you can aggregate those decisions in general and then see how the features that we have used in your image contribute to the decisions of your networks. For example, here you can see the two networks that we discussed about previously. For this network, the thing that leads it to most false positives is the displacement on Z, as opposed to this network that is the control input in Z. And so depending on the task, depending on the final application, this can help resolve and evaluate if the model is appropriate for this task or not by predicting how its behavior is going to be and what will affect it when it's executing its task on the real world. And that is all for me, and thank you.